Hello. I want to add some more results and some more another example of usage of Aumann expectation, something that I left from the previous video. So first of all, let's say that we have a X, okay, a random set, okay, which is defined on a probability space omega, descript F, sigma algebra, and P probability measure. Okay, random set on this probability space. Okay, and for any, okay, so for any, let's say A, which is a measurable set, so it's in the sigma algebra, let 1A, okay, of omega just be equal to 1 if omega is in A and 0 otherwise. Okay, so those indicators, and we know that this is a random variable, so that's a measurable mapping from this probability space to the real numbers. In this case, it's just binary. Okay, so the following result states the following, okay, that small x, a regular random variable, okay, is in the selection set of x, okay, if and only if, okay, the regular expectation of the random variable x times 1a, okay, is inside the Aumann expectation of the random set capital X times 1a. Okay, so first of all, this is okay. We can, if the expectation of X exists, then this expectation will exist as well. Okay, and here this is a random set as well. Okay, let's just make sure that we understand why. X times 1a of omega, okay, is equal to, okay, we will define it as x of omega if omega is in A, and just the set that includes the point 0 if omega is not in A, or it's in the complement of A. Okay, so this is a way to characterize, and the important part here is that for all A in the sigma algebra. Okay, so this has to be true not just for one A that you can find, but for every measurable set inside the sigma algebra. If this condition is true, then if this is always true, then X is in cell of X or the selection of X, and vice versa. If X is a selection of the random set, then this must be true for every set A, measurable set A. The second result is about convexity of the Aumann expectation. So let's start from X, which is a random set on this probability space, and we are going to assume in addition, okay, a non-atomic probability space. Okay, so non-atomic means that I cannot find a single omega, small omega inside capital omega, such that it has a positive, a non-zero, a positive probability mass. Okay, so there are no atoms in this probability space. Now, the more important result or the consequence of being a non-atomic probability space is that, okay, so that means that for any alpha in the 0-1 interval, okay, and the numbers 0 and 1 are the easy cases, but it's true for any value between 0 and 1 as well. So for every alpha in this range between 0 and 1, there exists omega 1, which is a subset of omega, such that P of omega 1 is exactly alpha. Okay. Of course, if I want to create 0, I just choose the empty set, and if I want to create 1, I will just choose the whole omega, and that's the easy part. But any value between 0 and 1, I can find omega 1. And of course, this also means that the probability of omega 1 complement, which is also in the sigma algebra, okay, is 1 minus alpha. Okay. So now, how can we use that? Okay, so the claim is that if X is a random set on a non-atomic probability space, okay, comma, then the Aumann expectation of the random set X is a convex set. Okay, so I'm not going to show a proof of this general result. I'm going to demonstrate this claim, this theorem, with a simple example. Let's see the following example. So let x1 and x2 be two regular random variables, okay, on omega phi p, a non-atomic probability space. Okay, let X be the following random set. We are going to take x1 and x2 and put a curly bracket around them. Okay, and I'm not claiming that x1 is always less than x2. It's just two random variables. Can be independent, can be independent, can be anything. Just two random variables that I put curly brackets. Okay, so for every omega, okay, x omega is two numbers, x1 omega and x2 omega. And of course, you can see that x itself is not a convex set. Okay, it's just two distinct points in R. Okay, so I can be generalized to RD, but for simplicity, okay, all random variables are R-valued. Okay. Also, without loss of generality, assume or let the expected value of x1 be less than the expected value of x2. In other words, I'm going to label them or name them such that their expectation, the expectation of x1 is less than the expected value of x2. Then, okay, the Aumann expectation of x, which is not convex by itself, okay, is equal to the whole interval E of x1, 1, to E of x2. Every point in between these two expectations, not just these two expectations. It's easy to create these two points by themselves. Okay, I just take a selection which is always selecting x1, I'm getting this point. I'm taking a selection which is always taking x2, I'm getting this point. But I'm saying I can create a selection that will give me any value between this number and this number. So suppose this is 3 and this is 4, I can create 3.72. Okay, so let's see a proof of it, which is relatively simple. Okay, so any, okay, let's call it proof. Okay, let's call it y be in the interval E of x1, E of x2. Okay, then we can find some number alpha such that y is equal to alpha times e of x1 plus 1 minus alpha e of x2, and this is because this interval is a convex set in R. Okay? If we have this alpha, we remember the previous result, so there exists, okay, so we can find omega 1, which is measurable in omega. Okay, I should have said before that omega 1, yeah, it's a subset of omega, but it's also inside the sigma algebra, okay, such that the probability of omega 1 is exactly alpha. So now I'm going to create a selection, okay, so let x alpha, okay, be equal to x1, okay, if x1, if omega is in A, and x2 if omega is in A complement, okay? And this is a random variable, okay? It's going to pick a point either in x1 and x2, so x alpha is always going to be in x, okay? And it's a measurable one because omega 1 is a measurable set and x1 and x2 by themselves, okay? So I can write, basically, I can write y, okay? I use this for the value, so let's call it y bar, okay? Let y bar, okay? So that's a number, but the random variable y will be equal to x1 times 1 of A, okay, or I called it without square brackets here, but okay, you understand that this is A, sub A, okay, and 1A, the indicator for omega being in A, plus x2 times 1 A complement, okay, that's basically this definition, okay, actually, yeah, so this is, if I call this y, okay, and yeah, no need for a new notation, this is x alpha, okay, basically that's another way to write x alpha, okay, the expected value of this x alpha is going to be equal to this y bar that I'm looking for, okay? Because again, that's how I defined. I'm going to take the expectation of this part that will give me alpha times the expected value of x1, and I'm taking the plus the expectation of this part, which will give me 1 minus alpha times the expected value of x2, okay? And that will create the y bar, which is written here, okay? So that's how I can create any value between this lower bound e of x1 and this upper bound e of x2. I just select enough x1 enough times and x2 enough times in this sense, okay, such that the expected value of this selection will be exactly the point that I want in between these two values. Okay, so this is why I can get a convex set. Now, of course, if I generalize this to RD, I would get here is R2. Okay, 2 points. Okay, this will be done coordinate-wise. So on each coordinate, I can recreate this. So if this is 1 point and this is another point, this is the expected value of x1, and this is the expected value, okay, of this is the expected value of x2. Okay, I'm connecting a straight line between these 2 points. Any point on this line, okay, this point, for example, is an alpha 1 minus alpha convex combination of the x coordinate and the y coordinate, or the first coordinate and the second coordinate, and therefore I can do what I've done here coordinate-wise and do that also for RD. Okay, so those are 2 important results, especially the convexity, that will be very useful for us, as you will see in the next video. Thank you for watching.